All right. And there are indeed some people. All right, just mute them. And that looks good. This is going to the right thing. All right, I should be okay. So there's a bunch of interesting news stories to talk about. This one I thought I was very interested to read about. For about 20 years, BGP has been fantastically vulnerable. Mudge talked to Congress about it and everything else, and I've heard that there were proposals to improve it, but none of them have been gotten to deployment. But apparently one of them has. Something called RPKI is some kind of DNSSEC type improvement for BGP. And Cloudflare now supports it and has a toolkit you can install on your machine, so your BGP routes are cryptographically authenticated, which would be a great improvement in security if it works. So we'll see what comes of all this. It sounds pretty complicated. Sounds a lot like DNSSEC, which is very annoying, a lot of work for people, and many people don't bother deploying it for that reason. But there's a lot of BGP hijacking that goes on, a lot of BGP mistakes that go on that reroute large amounts of traffic. So it would certainly be nice if something like this became widely deployed and started working. Somebody deployed this list answering the question where people say, how do I get started in security? So there's a long list of resources here. So, and recommendations with CTFs and training materials and all that. So that might help people. So I put it on the news links. There are many, many people that have written various ways to get started, and even these classes are in here someplace. So that's one place for beginners to take a look. This is one I had never heard of before. They infect your phone and then play invisible videos to drain your data. I think the point is it's ad fraud. Those videos are being treated as video ads and they're getting paid money for them, but it's so much that it uses up your data and you exceed your bandwidth cap and all that stuff. So that's DrainerBot. Somebody is splicing how to commit suicide in the middle of little kids' cartoon shows on YouTube, and various parents have seen it and certified it, and now people are freaking out and blaming YouTube. Other people are putting pedophile in the comments of videos on YouTube, and YouTube is having a big scandal, a little bit like Facebook's scandal a few months ago, where everybody's really, really, really mad at them for not censoring their platform more. So we're getting more and more professional censors. This reminds me, when I was a kid, there was the comic book code, and some of the similar code for TV that you couldn't have, like on television, every time anybody had any kind of magic, it all had leader disaster and stuff. And then there was one that came out 20 years later where every time someone fires a gun, they can't hit anybody. And they have all these rules. So anyway, we're going back down that path. So these are two Russian cybersecurity chiefs, one from Kaspersky and one, I think, from their government. And they both got like 22 years in sentence for treason for leaking something to the FBI, which is still not clear. They've been having secret testimony in a secret trial, and they leaked something, and people are trying to guess what it was. Was it something about hacking the DNC, or what was it? But anyway, they did something and got a long prison sentence in Russia for it. And so it'll feed the conspiracy theorists. So the anti-vaxxers are really hitting the news because I think 130 people have now got the measles because they refused to vaccinate their kids. And what these guys found out is if you're a legitimate medical institute and you put YouTube videos up on why you should vaccinate your kid, immediately after that video, it plays anti-vaxxer videos. And this begins, I think, at least helps me understand the problem with the algorithm, which is, of course, the same reason why I've learned to never even bother talking to journalists about anything I do, because everything I do is too dull. A story about how you should vaccinate your kids is dull. A story about how vaccines are poisoning your kids is exciting. So when they go for the one that gets more thumbs up and people like and brings more people in to watch the ads, they will always go for the more controversial, insane thing, which I think helps to explain our politics, where we end up with extreme loudmouth views instead of reasonable people getting most of the attention. So apparently, Cyber Command disrupted the internet access of the Russian troll factory. There's a famous one called something, Internet Research Agency, which is what sends all the fake social media profiles to make everyone angry about things like gun control and abortion, or blaming Hillary Clinton, or whatever is the hot thing at the time. And they apparently took them offline for a while with some kind of cyber attack. So that sounds pretty good, but most everyone agrees that this is really pretty trivial and not significant enough to really stop them for long. But it does show, I think, a step of the US becoming more aggressive in the field of cybersecurity. So this is a recurrence of an old problem. When Amazon first brought out E2C and started leasing out servers, somebody tried a forensic tool and found out they were not wiping the disks. So you could deploy a new server, look at the disk, and find the previous person's data. So Amazon fixed that. But what these guys find is, of course, if you can rent a bare metal server in the cloud, and if you do, you get your own motherboard and you get your own firmware on the motherboard. And now there are firmware rootkits that live in the firmware, not in the hard drive. And of course, nobody is scrubbing that, because that was considered pretty exotic, and these guys showed that you can rent a cloud machine, put malware in the firmware on the motherboard, and then wait for it to be deployed to somebody else, and then you can control their box. And they, for their research purposes, they rebought the same box again later to show that they still had the malware on it. So IBM said they're now going to scrub that for this brand of motherboards. That's the reason why this stuff never gets very far, because these firmware rootkits are hardware dependent. So they told you have to go to other machines with the same brand of hardware. But cloud providers have a whole fleet of things with the same brand hardware. So it's more effective there than it would be trying to affect random people's laptops. Anyway, so you can connect, if you can connect your Mac to a hardware device, like through USB-C or any similar connection, it has direct memory access, it always has, bypassing the operating system to make it faster. And that means you can totally pwn the box through it with Spectre and Meltdown. Because if you can write directly to RAM, then you can totally take over the box because of this speculative execution vulnerabilities, and they've demonstrated this. So some people don't care about this because you can't do it over the internet. You can only do it if you get physical access, but if you could just get someone to plug in a USB stick or a phone or a camera or something that was malicious, or manufacturer devices, like people worry about supply chain attacks. If you just put some kind of malware in a commercial device, you get them. Yeah.
I had a question about that. I've seen a lot of bug bounties where they don't accept like man-in-the-middle attacks. So
yeah.
What's the reason for that? They just feel like it's so impractical? Or?
Almost all bug bounty programs that I've seen are really essentially fake. They're so limited that you can't do much. They have a very, that for better or worse, that's the way they always are. And most people I know that do bug bounties get very, very frustrated because the rules are very strict. Everything you do is determined out of scope, and everything else, they say somebody else found it first. So very few people actually make much money. A small number of superstars get the money. The rest of the people, it's intrinsically kind of nuts. I mean, you have to be the first one.
Yeah. So
it's really only for the rock stars of the world. It's not, I mean, the rest of us should just get a normal job, I think. But anyway, yeah, I know they, of course, what happens is you get a whole bunch of reports on all kinds of crazy things. So they somehow focus their attention on what they want. I think it's a new thing, and people are very unclear how to really get benefit out of bug bounty. And you really need consultants to help you organize your bug bounty, or you'll just end up wasting your time and money.
You're at that fine line of, am I doing research or am I admitting a crime to a company?
Well, that's what the bug bounty gets you out of. If you obey the rules, then now, but so it protects you to that extent. You're not going to get prosecuted. But from the company's point of view, they're going to get a flood of reports. Most of them are going to be useless. Now they have to pay someone to screen all that. And that's why partnering with a company like BugCrowd that will do that for you is probably the most reasonable answer. And they will guide you to try to get some good out of it. So it's increasingly something the bigger companies do and get some good out of, but they all say you can't just jump into it. You have to really prepare for it, or you'll end up just wasting your time and your money. So I heard some students getting excited about this. There's a new 4G and 5G attack that can locate your phone. But as I thought, they went through it. It's really very impractical. It relies on getting a lot of data and being able to intercept the phone in a known location and having an ISMI capture and DOSing the normal communication signal so it sends you another. It's pretty extreme. In principle possible, but in practice not something to really worry about much. And I think I'm going to skip the rest of this so we can get down to the chapter, because this is exciting stuff. I'm very pleased with this textbook more than ever. This guy, and especially in the next chapter, this guy is one of the world's leading cryptographers. He's inventing the new protocols that are better than the ones that got approved. So he really knows his stuff. And I can tell in this book takes stuff that my previous book glossed over as too difficult, and he makes it easy to understand. So I'm really pleased with it. Anyway, so stream ciphers. We'll talk about these. And here's the game. A stream cipher is a symmetric key. Both block ciphers and stream ciphers are symmetric. And you have a secret key, which is shared by the sender and receiver, and the block cipher takes blocks of plain text and mixes it with the key and turns it into blocks of ciphertext. But stream ciphers take the key to produce a stream of bits in a pseudo-random way. And this is why a student asked a couple of weeks ago, which I thought was a very good question, why don't we just use the one-time pad? And all these things are a way to solve the key distribution problem for the one-time pad. So the stream cipher is a way of delivering a small key and then creating something that is kind of like the one-time pad bit stream out of it. That's the idea. And of course, it's not perfect, but it's a practical way to do an approximation of that. And so you have this long stream of pseudo-random bits, and then you XOR the plain text with the bits. So it's essentially the same thing as a random bit generator, only a deterministic one, not a truly random one, so that you can have a seed and generate a pseudo-random bits, and somebody else with the same seed will get exactly the same bits. That's the point. Otherwise, you wouldn't be able to decrypt it. Now, you also need a key and a nonce here for most applications, because usually you're going to keep encrypting more and more and more messages, and you're not going to have a way to keep distributing more fresh keys. So what you do is, instead of having a different key for every message, now if you were to reuse the same key for another message, you'd have the same bit stream. And that would really be bad. As we'll see in a project, the two-time pad, if you use the same key stream even twice, then everything is shot. So you have to have a nonce, which is the additional thing you add to the key every time, so that you have a different bit stream for every message. And that's important here. And the nonce is not a secret. It can be sent in plain text along with the ciphertext. But since you don't know the key, you cannot deduce the bit stream from the nonce. That's the idea. That's how it's really done. If you were to reuse the nonce and the key, then you would have two messages with the same key stream, and all you have to do is XOR those two messages together, and you eliminate the effect of the key. So now, the XOR of the two plain texts would be equal to the XOR of the two ciphertexts. And if there are two situations in which this is very effective, well, really quite a few. If the plain text, for example, is readable English, then you can just start guessing words and pretty soon find it. If they're Microsoft Office documents, large portions of it are just zero, and 0 XOR something is not unchanged, so a bunch of it will just turn into readable plain text. Terrible things happen if you have two messages with the same key stream, with the same bit stream. And that's the point here. So, and that's what this does. This is the two-time pad. You take a one-time pad and use it twice, and here you can do a sliding key attack and totally get in, and that's what this book is about. That's how they cracked the Russians' use of one-time pads, because they were under pressure in World War II. They reused their one-time pads. They couldn't generate them fast enough, so they put in more copies of carbon paper, made like 4 and 6 copies of them. And so their small number of messages intercepted actually used the same pad, and that was enough of a hole to crack the whole thing open after years of diligent mathematical work. So, all right, so two kinds of stream ciphers. The stateful ciphers have a secret internal state that is changing as they go, and the counter-based ciphers use a counter instead. And so the state will be initialized with the key and the nonce. So you have two functions. The initialization function starts the state, and then you have an update function that is called over and over and over again to create more and more and more bit stream. So the counter, you do not have a state, you just have a counter that's on the outside, and you just keep incrementing the counter, and that is what causes each batch of bit stream to be different than the previous one. So there are originally, all these things date from a really long time ago, like the 50s and 60s, when computers were really weak and primitive, and you would have things like actually putting transistors in one by one and worrying about how many transistors it takes to get the job done. So they had to use dedicated hardware, which of course we've gotten back to thanks to the cryptocurrency people, where you have to be as fast as you possibly can. So even though computers are much faster, you still are competing to get super fast. So you use these ASICs or PLDs or FPGAs, different pieces of hardware that can be dedicated to one task. And so your hardware implementations typically work on bits one by one, and you count the number of gates it takes. Software implementations use processors that work on 32 or 64-bit words, so basically everything works in blocks of bits. And that means different kinds of algorithms are optimized for the different platforms. So the original, back in the old days, the point was you had to build hardware devices, and this is true now with the case with Internet of Things. In the early days, they were thinking of adding machines and modems at banks to move data around, hardware devices that would sit there. Now it's the Internet of Things, and the cryptocurrency miners. There are a new generation of hardware with baked-in cryptography that wouldn't be ever change. You're going to keep just trying to do the same algorithm over and over, super fast. So that's the game here. And you see, in the old days, the stream cipher would take 1,000 gate equivalents, but a software-oriented one would take 10,000 gate equivalents, and that would make a big difference in money long ago. It isn't such a big difference in money supposedly now, but I think that's all coming back again because of the Internet of Things and the cryptocurrency miners that are again pushing you back to these hardware-oriented things. Anyway, DES was optimized for hardware. At that time, general purpose computers were not what most people were using. They were mostly thinking about infrastructure components that would be installed in banks and other companies, and you would buy an encryption device and you would send all your data through the encryption device, not that you'd have a general purpose computer doing it. So it was designed for that, and that's why DES is not very fast when done with a processor. AES is faster and more secure, of course. So here's some data from, I think, within the last year about the Bitcoin situation. So your ASIC is the fastest and 100 times faster than CPU. GPU is not as fast, but cheaper, and that's why I think it became extremely popular. And this is why I think until about a month ago, you couldn't even get GPU cards. They were totally all bought up by the Bitcoin miners. And the only reason they ever became available is because the price of Bitcoin fell to where the miners didn't grab them up so fast. And now you could actually get them to play games again.
It'd be Ethereum for GPU.
Yeah, Ethereum. Yeah, Ethereum. Anyway, so and CPUs are been too slow to keep up, except for the smaller coins. So a shift register is what you use for this. And here's a shift register. The left shift operation is right there, less than 1. So if you shift to the left, the highest one falls off, and that becomes your output, and a 0 comes in from the right. And as you keep shifting to the left, you gradually pad it to the left. So if you start with 170, that's 1010, you shift it to the left. Now the 1010s move to the left, you have 2 zeros, 3 zeros, 4 zeros, and on you go. And so the output is coming out. So now if you use this kind of shift register, if you have 8 bits, you're only going to get 8 bits of output before it's all 0. So that's a shift register, which is not very useful. What's more useful is a feedback shift register, where you have some kind of system to keep refilling pseudo-random bits on the right so you can keep it going. So you have a function that is used to fill in the bit on the right every time you shift. And that somehow calculates a new bit from the state of the register, and now you can run it longer before it repeats. So here's a 4-bit example, 1100, and your function is just XORing all 4 bits. So 1 XOR 1 is 0, and XORing things with 0 does nothing, so this bit is 0. The next time, let me shrink this down a bit so I can point to it more accurately. All right, and I'm gonna see if there's a chat message here. There is. Okay, is redirecting to HTTPS from HTTP on servers a bad practice? Yes, it is. It's a very bad practice because you can hijack the connection at the point where it's HTTP, so it never does redirect to HTTPS, and the user probably won't notice. And here is a performance difference between stateful and counter-based. Yes, counter-based is more easily parallelizable, so I suppose it would be better, but I think you really have to get down to specific choices to make but in general, yes, I think just like in other things, the counter-based is more likely to be faster because you run it on parallel processors. Anyway, so here we got 1100. So if you take the XOR of all those, you have 0. So we're going to shift to the left. This 1 will fall off, and you have 0, 0, 0. Now next one is going to be 1 because 1 XOR 0 XOR 0 XOR 0 is 1. So you put a 1 in here. Now it's all zeros. This one's 1. Now it's going to be 0. Now it's going to be 0. And on you go. And you notice now we're back to our original state, 1100. So it's just going to loop forever. So this has a period of, I think, 5. 1, 2, 3, 4, 5, right? It's just after 5 times you're back where you started, and that's it. It's just going to go over and over. And that's true of all linear feedback shift registers. They don't go forever. They only have a period of so long, and then they repeat. So here's how this one looks now. By the way, since there are 4 bits, there's actually 16 possible states. So you might imagine that you could get 16 bits out before it repeats, but it isn't actually working that way. This particular algorithm gives you 3 cycles of 5 and 1 that just sits there. So it is not a maximal linear feedback shift register. It does not have the longest possible period. So that's the game. Typically the F is the XOR of some functions. That's what's linear. And so this one is a period of 5. The longest possible one is 2 to the n minus 1, because if all you're doing is XORing bits, Then if you XOR zeros, you always get 0. So you always have 0 sitting here all alone, repeating and never changing. So the most efficient one you could possibly make is the one that would put all these in one big loop. That's the maximal linear feedback shift register. So here's another one. If you only XOR bits 1, 3, and 4 from the right, where these ones are, but you skipped that one, then you have this diagram. You can see XOR 1, 3, and 4, and 1 are XORed together. So if you start with 1, you're going to take 1, 3, and 4 and XOR them, so we get 1. Shift it to the left, 1, 3, and 4 is still going to be 1. Shift to the left now, 1 and 3 are 1s, so we get 0. Shift to the left again, 1, 3, and 4, it's 0 again. Shift to the left, 1, 3, and 4 is 0 again. And when we shift to the left, 1, 3, and 4 is 1 again, and now we're back to 1. So now the period is 6. There's a minor error in your textbook that he fixed in the errata, but anyway, this one has a period of 6. So it's, again, not maximal, but it's a little longer than the last one. So here's one with a maximal period. All you do is XOR bits 3 and 4 and ignore the others. So if you start with 0, 0, 1, you have 2 zeros, that gives you a 0. These 2 zeros gives you a 0. 0, 1 gives you a 1. 1, 0 gives you a 1. And so if you work your way through, you get all these 16 cycles to get back where you started. So that it is 15 different numbers. The 0 is not here. So that is the maximal period. And all right, so that looks pretty good, but in fact, it's terrible. It turns out that all you need is the n outputs. So if you have a 4-bit shift register, you only need 4 in a row to uniquely determine which one it is. So in practice, this is no good at all, and there's an algorithm for that, the Burke-Massey algorithm. Because you can convert these things to equations, and with a few measurements, you have a few equations to solve, and it's enough to determine all the constants. So you have to have something nonlinear to make it hard to solve. And so what people do is take linear feedback shift register down here, and then add a nonlinear function here. This is one simple, a filter function. And the filter function will just use something like and or along with it, something like this, where it takes these two and those two and then XORs them here, so that that is something other than just a simple XOR function. And that's better, but still breakable with more complex attacks, algebraic or cube attacks or fast correlation attacks. These are interesting to talk about because they are going to come back again and again as we proceed. The algebraic attacks are the mathematical ones solving the equations, and those are, of course, the most deadly if they work, because you might prove that the entire category of math can be cracked. Cube attacks are similar, using derivatives and analytic. The fast correlation attacks are more like the brute force attacks, where you just make an approximation of the math and get close and then correct your errors. This is why if you look at what happened to WEP, which we're going to get to, in WEP, you used a algebraic solution to eliminate some of the keys, and then you just do a brute force of the remaining keys. So the two are combined.
Are these algorithms still being designed to be efficient on hardware components?
Yes.
Okay.
Yeah, that's the point of these. You build these literally out of those gates in hardware. That's why this, you can see, it's very much tied to hardware. Yeah. And so what's best is to make a nonlinear feedback shift register where you don't use this XOR function at all. You have a nonlinear function, mixes XOR and OR. And if you make it, this makes it very hard to analyze mathematically and helps stop those mathematical attacks. It's so hard to analyze, you can't even decide if it's got a maximal period. You can't calculate which functions might have a maximal period. So what people found to be the solution is to mix LSFRs and NSFRs together, because the linear feedback shift register, you can analyze and prove that it's maximal, and the nonlinear one is hard to crack. So if you combine the two of them, you know it has at least a certain period, and you know it's hard to crack. So that's pretty smart. And you see, this is why, you know, AES had those 4 different kinds of transformations. This is how all these secure systems work. You have several transformations so that it is not easy to crack by cracking one of the components. And that's what Grain 128 is, which is modern and considered very secure. So you have 128 bits in the linear feedback shift register in its maximal, so it's got 2 to the 128 minus 1 period. You've got a nonlinear shift feedback register and a nonlinear combination function, and those give it strength. So you feed this thing 128-bit key and a 96-bit nonce, and it fills in their missing 32 bits with zeros and ones. And now you've got something that can be used for an enormous number of messages, 2 to the 96 messages before you repeat the nonce. And the feedback function just combines a strange mixture of bits. And here is your ridiculous nonlinear function. Yeah, there, which is really pretty baffling. It's got like 4 multiplications, 3 multiplied together, 2 multiplied together. That's pretty baffling. You wouldn't want to try to solve that analytically, and that is the whole point. It scrambles things in a way that you're not going to easily figure out mathematically what that did, especially after you iterate it against itself a few times. So this is considered very good. Quite modern. 2006 is not very old at all for these things. And the original version had some side channel fault attacks, which I mentioned before. It means not that it's broken, but that if the processor drops a bit while calculating it, then that has an effect that lets you deduce things. So all the algorithms I thought are vulnerable to that. I know RSA is, but anyway, they didn't like it and they proposed 128A to fix that problem. And this one apparently has no known attacks at all of any significance. So it is out there. It's being used in some proprietary systems, but it's too new, I think. This is true of all standards in technology, and including cryptography. Once something that is good enough appears, usually something better comes out and nobody cares. They just stick with the one that they know until it is really broken, which is, understandable. And then this chapter began to help me understand why cryptographers hate the government so much, because there's a whole crypto wars. Cryptographers are so angry at the government, and there's much more rotten stuff the government did than I ever knew. A51 is what's used for mobile phones, even still. And A51 was created in 1987, but kept secret, sold to the phone companies, kept basically as a secret until it was reverse engineered and leaked decades later. And this is because of the spy agencies. They wanted to be able to intercept phone traffic. They didn't want anybody to know. So they not only kept it secret and made sure it was weak enough they could crack into, but they also had a special version to export that was even weaker. So all things shipped to countries they don't like were deliberately even more breakable, A52. And this has happened over and over again. And the crypto people are very, very angry about it, because once you release some equipment with deliberately bad cryptography, you sort of poison the world, because that junk is on the internet and a bunch of other things have protocols to interoperate with it. And you've created a whole, it's like virus infected machines. You've created a dangerous group of bad citizens on the internet that are going to keep having echoes through the decades of problems coming from it. So this was leaked in 94 and reverse engineered in 99. And it was used by 7 billion people in 2014, and a lot still, because if you're using the older phone protocols, this is what's used for encryption, and it is incredibly bad. The NSA can routinely crack it, and that's because it's really simple. It uses a total of 64 private bits in 3 linear feedback shift registers. That's all. They use these functions, and that would be completely linear and totally crackable after just 32 bits of data coming out. The only thing that's nonlinear about it is it doesn't update each one of these with every clock cycle. It takes a few bits and combines them to pick 2 of the 3 to update every clock cycle, and the other one doesn't update. And that turns out to be a nonlinear activity. That's the only thing. There's the algorithm of it. So that irregular clocking thing makes it a little stronger than an LSFR. Well, quite a bit stronger than an LSFR, but still not as strong as it should be. So there's a brute force attack where you try all 2 to the 64 keys for 2 to the 64 operations, and that's very impractical. But if that was the only weakness, it wouldn't be too bad, but there are much faster attacks. There's subtle attacks and brutal attacks. And the subtle attacks try to use mathematics to try to lower it down. And it turns out, this one here shows, if you do not just try all combinations of 64 bits, but you look in more detail at the inside, where there's 2 to the 19 of this and 2 to the 22 of that and 2 to the 11 of that, and only try them this way, you end up taking fewer tries by paying more attention to the internal structure. This gets you down to 2 to the 52 operations, which is a lot less than 2 to the 64, but still pretty hard. But the really tough one is the time memory trade-off attack. Now, I remember hearing about this about 8 years ago at DEF CON. Someone was going to make the 2 to the 64 table, and I think this is the thing where I'm finally reading in more detail here. So you could try to make a complete table of 2 to the 64 bytes, but you can't. You could do the calculation, but you can't store the data, because 2 to the 64 bytes of RAM is 256 million terabytes, so that's an impossible amount of hardware to buy. So you cannot make a full time memory trade-off table where you have the entire crypto system in RAM and you just look it up. But what you can do is put part of the calculation in RAM, so you have to do less calculation cycles per cycle and speed it up. And that's how most time memory trade-offs work. Like you could have a logarithm table in RAM or a multiplication table in RAM, and that would speed things up. So you take part of the calculation and put it in RAM, and that's what these people did. They took 2 months of calculation so they could do 2 to the 64 calculations, and they made a table that was only 2 terabytes in size, but did a lot of the calculation, and that made the brute force attack much faster. This is how time memory trade-off works. And so now, using GPUs running 100,000 instances together, they were able to decrypt this thing in real time. So you can hear, you can tap phone calls. And that's pretty awesome, but that's the point of these things. And this was abandoned for later networks and replaced by the Kasumi. And people are strongly concerned that the NSA has also poisoned Kasumi with a backdoor. And it helped, like I say, helped me understand the perennial bad attitude cryptographers have towards the government. They've done a lot more poisoning things than I understood. So is TMTO like rainbow tables? Yes, it is exactly the same thing. Rainbow tables are what these things are called in hacking tools for hashes. It's exactly the same. So the Microsoft early password hashes used before Windows XP, LM hashes, you could make a rainbow table that solved all alphabetic passwords, and you could fit the whole thing in RAM. So it made the attack essentially perfect. Even the newer algorithm, NTLM, there are rainbow tables you can make that make the cracking faster, but it's not as perfect. Yeah, good. And so I got some Kahoots. Let me bring them up. That is here, 6A. And we should have some Kahoot music. There we go. All right. And I'll wait a few more seconds, see if we got any more. These are the usual suspects I see. Looks like it. All right. So, which one uses init and update? There's the stateful ones. They have an internal state you initialize, and you keep on updating as you pump out blocks of keystring. Which type was designed in the 70s for hardware? Yeah, that was DES, designed for hardware, not very efficient in general purpose CPUs. Which one do you break with Berkeley Camp Massey? Which I think I spelled wrong. Yeah, that was the linear feedback shift register. That's an algorithm for solving the group of equations needed to deduce the key, essentially. All right, and which one uses a linear and a nonlinear feedback shift register? That's Grain 128, which is apparently very good. All right, so I got M. Dot and Jeff. Good, real names. I know M. Dot, that's not a real name, it's close enough to a real name. People I know, good. All right, so we're still on track to just keep going here. So then we can talk about the software-oriented ones. And so these work with 32 or 64-bit words instead of bits. and are therefore designed for CPUs. Stream ciphers have become more popular. There has been kind of a damned if you do and damned if you don't. First, everyone went to block ciphers to get away from the problems with stream ciphers. And then they had huge problems with the padding oracle attacks on block ciphers, so they would go back to stream ciphers. Then they would find more problems with stream ciphers and go back to block ciphers, and we sort of wandered from one to the other, back and forth. It's sort of like Windows versus Linux. There's no simple answer. So anyway, RC4 was designed by Ron Rivest and again kept secret, and it was not leaked until years later. This is the stream cipher everybody uses. It is actually fantastically brilliant, and I was very pleased to learn about it. I heard about it for years, but I never saw such a clear explanation. And finally, in the last couple of years, everyone has given up the hope on RC4, and they're trying to remove it from everything. They're finally get fed up with its long, notorious history of weaknesses, but people used it anyway. It is fantastically brilliant. And I'm surprised your book didn't explain it this way. It's just like a deck of cards. You start with all the possible bytes, 256 of them, and all you do is shuffle them around the way you would shuffle a deck of cards to make the key string. No XOR, no OR, no AND, no math of any kind. All you have is just a way of choosing which two cards. The key determines which two cards to flip. And then you flip the one, flip the next one, you flip the cards many times. And after that, you shuffle the deck. But since you did it in a way chosen deterministically from the key, the other person can shuffle the deck the same way and create the same key stream. So just with this very fast operation of just shuffling the bytes back and forth, you create a pseudo-random looking stream, and depends on the key. And it's very fast, very simple, and you see why it got so popular. And it was considered secure for a long time. It took people a long time to find the problems with this, but when they found them, they were really serious. So if you want to encrypt plain text, it takes the shuffled cards and generates M bytes of key stream by, again, flipping things around. No XORs or anything. So this is what WEP uses. Now, the problem is, to actually use this in a real situation, you cannot use it as it was designed. It was designed, for example, with no nonce. And WEP is a very difficult thing because you're encrypting wireless frames. And one of the huge problems with wireless frames is that almost all of them are identical. The most common network packet is an ARP. All the ARPs are easy to spot because they're much shorter than all of the packets, and they're all almost exactly identical. Most of them are completely predictable. So you have many, many repetitions of exactly the same plain text coming out that you can just guess. And so you need some way to have a lot of nonces. And the problem is there's no nonce in this design. So they tried to ram a nonce in by putting the first 24 bits of the key and treating it as a nonce. And this is the kind of thing that always ruins cryptographic systems, when you don't exactly match the assumptions made by the designers, and you try to ram something in the designer didn't really plan on, then you're very likely to create a disaster, and that's what happened here. The first problem is a 24-bit nonce is too short. Now, the best thing would have been to just count forward, 1, 2, 3, 4. Then it would take all the way to 2 to the 24 before it repeated, but even that's not very long. But a lot of people used random ones, and random ones will hit a duplicate after just 2 to the 12, which is only 4,000 packets, which is a very short amount of time. When we cracked WEP, when we did it, it only took about 5 minutes or 10 minutes to get enough to have some collisions. Yeah.
What you can do is you can send traffic to the router and have it automatically send you a bunch of ARP packets back.
Yes. Yes, that's what you do. Well, we never got it faster on our equipment than maybe 5 or 10 minutes, but yeah, you can. There's a whole series of attacks that got worse and worse. The original ones that required duplicate nonces took about 50,000 packets. There were increasingly brilliant ones, faster and faster, based on more and more patterns in the wire. So it turned out in the original data, and the nonce is sent in plain text, so you can easily pick the packets that have identical nonces, and the ones that have identical nonces have been encrypted with identical key streams. So all you have to do is XOR them together, and now you've got the XOR of the two packets. And so that's how you're able to quickly deduce something about the key and deduce the number of possible keys down to where you can triply brute force them, like 2 to the 30 or something, which is really not enough. So it turned out to be extremely fast to crack it, so fast that WEP was destroyed 2 years after it came out. People told me, I wasn't in the business then, they told me that the FBI went to the security conventions and demonstrated cracking WEP in 2001. And companies continued to use it with the blessing of the payment card industry up through 2013. to send credit card numbers, even when the two largest breaches in history were done by stealing credit card numbers right off the wire with WEP by the same guy, Richard Gonzalez. He got busted for the largest credit card breach in history, so he ratted out his friends and became an FBI informant. They let him out on parole, and he did it again. And the second time, he didn't have a friend in the world. The FBI hated him, and all the hackers hated him. But this is what I say. Kevin Mitnick said, this is like an addiction, this hacking thing. Even when you're not making money, even when you're going to jail, you can't stop. It's like a drug. Anyway, that was his case. So many attacks came more and more because there's so many ways to exploit WEP. So WEP got totally wrecked, partly because they used RC4 and also because they used RC4 improperly by trying to ram in a nonce that really didn't fit in there. And then TLS is similar. TLS didn't try to add a nonce. It used a session key for each session. That's why early versions of TLS like 1.0, you could get the session key from Firefox and you could put it in Wireshark and decrypt the stuff. And that's why the NSA is archiving so much data in Utah, because if that data was encrypted with TLS 1.0 or 1.1, I think, they really can steal the key a year later and go back and decrypt it all. So the problem here is the one that led to about 7 or 8 successive attacks. The problem is that RC4 is not completely random. It turns out that some of the bytes are not equally likely to be any things. The second one is 0, 1/128th of the time, instead of 1/256th of the time, which is twice as likely to be 0 as it should be. And that means there's an incredibly simple, brutal attack, which goes like this. All you do is collect billions of the same plain text encrypted over and over and over again with different keys, and then just look for the most likely bytes, and that you can deduce the plain text from it without knowing the key. Like the second byte is more likely to be 0 than anything else. So if you just get millions of them until you find out which byte is the most common, that is the plain text byte, because 0 XOR plain text doesn't change it. And the first 256 bytes are all colored. So there's a certain byte more likely than others. So you know the key stream byte, even though you don't know the key. And therefore you just get the plain text right from the ciphertext without knowing the key for the first 256 bytes. But you need an enormous number of encryptions of the same plain text, like millions or billions of them. So people argue it's impractical, but they made them smarter and smarter. I went on WikiLeaks and just see them. I see them in news every year. Somebody comes up with another RC4 attack for TLS for about 10 years. And that's why people kept going to other ciphers and coming back, bouncing from one to another. And the one that really ended it all was the No More attack, when they finally said, all right, we're going to just kill RC4 at this one. So there's a nice website talking about the No More attack. You inject code to generate requests. You gather the encrypted requests. Then you calculate the likely cookies. And they tried to make a realistic situation where you're connecting to a real HTTPS website and getting a cookie. There's 16 characters. And they're going to get enough data to crack the 16 bytes of that cookie, which is totally going to get you into somebody's session. And they found a way to do it in like 75 hours, assuming you can do 4,000 requests per second. So you get the necessary millions and millions of things encrypted the same way with different keys that still have the cookie. And so that this would be a game ender of a exploit. And anyway, the accumulated effect of all these exploits. When you're in the vulnerability business like I am, or report things to people, it's often frustrating if they don't fix it. But it's the same as changing, political attitudes towards gay people or something. You don't yell at them once and they reform. You slowly erode them like water eating through stone. It takes years and years of repeated attacks before people finally get fed up with it and decide they're going to quit using this broken stuff. So anyway, then Salsa 20 came out, pretty exciting, the European competition. And part of what motivated me to teach this class is I went to PasswordsCon, which they merged with B-Sides Las Vegas a couple of years ago, and they brought in all these European cryptographers in this contest, and they were very interested, developing a new crypto system with all these advanced features. And I was real pleased to see such exciting stuff happening. And so this eStream was their contest in Europe, sort of like the contest we have here with NIST, to choose a new stream cipher. And so they liked Salsa 20. Salsa 20 was approved by them. Here's some others that were there. You see Grain was there in its earlier version. So Salsa 20 works like this. You take 512-bit blocks and you encrypt each one with a key, a nonce, and a counter. And in order to make it nonlinear, you add the original state back in. So you add, it has its own feedback. Instead of feeding back one block to the next like ECB, it feeds back this block to itself just to make it nonlinear. And so it has this quarter round function that takes 32-bit words, A, B, C, and D, and then mixes them together in a series of steps here. So this changes B, and when B is used here, it's the new B, and this changes C, and when C is used here, it's the new C. So these are in fact far more complicated than it looks like they are. And then you rotate them to the left, not just shifting, but rotating them all the way around. So the 0 wraps around for various amounts to, that's how you define bitwise rotation. So now you take a 4x4 array of 32-bit words, and you mix in here the K's are the key bits, the nonces are, I think, N's, then you have counters, and then you have some constant words. You mix in all these things, nonces might be the T's here. And once you've initialized all of them, then you have a series of transformations that are very much like AES. In fact, I spent a while looking for an animation. You could totally make an animation of this, and nobody's done it, which is annoying.
The same thing in the textbook. It looked like a big giant Rubik's Cube almost.
Yeah. And it looked, the AES had this nice, pretty animation, and for some reason, nobody made the similar animation here, but it totally is asking for it. So you transform them in columns, then you transform them in rows, and so the columns look like the thing on the left, where you're just mixing the colors across the different shades, and the rows are like diagonals, which is very much like AES, and that's exactly the same idea. You remove patterns one way, and then you remove patterns the other way, and so then you do have many rounds of doing this over and over. And remember, AES used 10 rounds, it also uses 20 rounds of all that stuff. And now this is very handy because what you can do is lower the number of rounds to get something you crack, and then try to decide how secure you are by figuring out the margin. And so it turns out that people have found various ways to crack ones up to 8 rounds, but nothing larger than 8 rounds. And so if you use either 12 or 20, as far as anybody knows, you're really quite secure. So things that can go wrong are all over the place. The simplest thing, of course, is nonce reuse. If you use the same key in the nonce more than once, it collapses immediately, as you can see with that project where you cracked the one-time pad. If you use the same key stream twice, it's very easy to recover the plain text without knowing the key. Microsoft Office did this, and WEP did it by accident by having a nonce that wasn't long enough, so it just happened to repeat. Microsoft Office did it by just forgetting about it. And so you can also just have broken implementations. You can make mistakes. I read this in your book, and I read it in the original source, and I still do not understand it, as a matter of fact. But this apparently has something to do with this swap function. The swap function at the top, the way I swap two variables is the sleazy way, where I make a third variable, set temp equal y, y equals x, x equals temp. That's how I do it. But if you don't want to make a third variable, there's this trick where you XOR, set x equal to XOR y, then set y equal to XOR y, and then set x equal to XOR y, and that should reverse itself. So it ends up swapping them without generating a third variable, and that makes it faster or consume less memory on certain implementations. And I thought this was perfect, but what your textbook says is, for some reason, if the x equals y, this produces a result of 0 when it shouldn't. And I struggled with that, and I could not understand it. If somebody figures it out, let me know. But they claim this was written by the part of the underhanded C contest to be deliberately broken C. And he says the error is up here. This somehow is not true when x equals y. And it sure seems true when x equals y to me. But he said the result is this looks like it's doing RC4 and shuffling the cards, but sometimes it just overwrites a card with 0. So after thousands or millions of computations, you end up with a key stream that is all just zeros. And you're not encrypting anymore. Stuff just comes out in plain text, which is cute, but I was not able to understand it, and I didn't bother coding it to see it happen in real life. Anyway, but that's a possible thing that could be wrong. Of course, you could just program it wrong. And the other thing I mentioned before, once you have a deliberately insecure protocol that you force people to use, then people try to pretend it'll be fine because we only make those nasty foreigners use it and our locals won't do it, but they don't think about international commerce, where we are going to buy products from those foreign companies and they're going to buy products from us, and we're going to ship computers back and forth, and pretty soon all kinds of people are using the stuff that only those nasty foreigners were going to use, And a bunch of other things have been developed from it, which can talk to both the natives and the forwarders, and therefore can be downgraded to the old stuff. And it turns out that many other things are using this deliberately broken encryption that, because it's sort of the same thing happens to the Great Firewall of China. The Great Firewall of China prevents people in China from seeing websites, and sometimes it does it by taking false DNS resolutions, where they look for a website and it tells them the wrong IP address, so they won't go there. And it turns out that other companies outside China, because of BGP, have their packets routed to DNS servers inside China, and the bad data leaks out of China and poisons DNS records in the rest of the world to some extent. It's just a problem. When you put something bad on the internet, it spreads like a disease and has unintended consequences years later. Anyway, so I got some Kahoots about that. And I have a lot more sympathy for the cryptographers that are just very, very, very angry at NIST and the NSA. Because mathematics in particular has this thing that if you start telling a lie even once, it sort of shatters the whole thing like glass. All right. All right. I think 9 is what we had last time. I'll wait a few more seconds to see if we got any more. Ah, okay. All right, I think maybe we got everybody now. Seems to be so. All right. All right, so what system puts a nonce value into the key? That's WEP. Turns out to be a terrible idea. It is not, you can't just choose part of the key and call it a nonce. You have to actually design a crypto system with a nonce because it's handled in a different way. And that turned out to be one of the really bad mistakes in WEP. Which one uses quarter round functions? Okay, that was salsa. You split things into 4 words, and then you go through 4 rounds of mixing those words together. All right, which one uses a session key to protect cookies? That's TLS. You negotiate a session key. You keep using a session key for a long session, at least in the earlier versions of TLS. All right, and which one uses 12 or 20 rounds? Salsa, 20. They're both considered very secure. Okay, so I've got WITB, and we know who that is now. And Caitlin again, and MDOT again. Good. All right. So these folks are 6. Wait, no, there. There. Caitlin and MDOT are 6. Good. And these other folks are 3. Okay. So I should mention we're going to cover it in the lecture next time, but I was very pleased. The next chapter I went through, and it was so much fun. I wrote a new project. So I'll just mention if for a good time, check out the last project, the row method. The row method we mentioned in the earlier textbook, and I didn't know what it was. We'll do it next time, but I'll just say a little bit about it now. The next chapter is about hashing, and hashing has this strange property. If you try to find a hash collision, the simplest thing to do is just take a long series of numbers like 1, 2, 3, 4, 5 and hash them all and look for a duplicate. And that will work. But this is the row method. And it's called the row method because this diagram looks like the Greek letter rho. And it goes like this. Instead of just hashing a series of numbers, you hash something starting value, and then you hash the hash and hash the hash and hash the hash, the way you would in password hash. And that is different because what happens is you'll keep getting different, essentially random numbers for a while. Eventually, you'll get one that duplicates a previous one. And as soon as you do, hashing it again will just go around and around the circle. So what happens is you go approximately, if your hash value has n possible values, you go approximately square root of n until you hit a collision. And then you go, the size of the circle is approximately square root of n, and you just go around and around the circle. And it turns out that this is useful in a variety of attacks. This makes a lot of things. This is essentially like a time memory trade-off. This way, instead of having to remember all the hash values up to a certain point, you can do a little more calculation. Because if you think about it, if you just remembered, say, every 10th hash value and waited for it to repeat, that would be enough once you hit the loop. And so even though you might have to do more total calculations, you will not have to remember a huge amount of hashes to catch a collision. So anyway, I just wanted to see this happen. This turns out to be incredibly easy to do in Python. With just a couple of lines of Python, you can calculate an MD5 hash, and you can make a short one just to make it easy. You can take just the last 2 digits with just putting 2 at the end, then you'll have a hash that's only 8 bits long. So the total number of values is only 256, so it's pretty easy to watch it go. And now if you just calculate a bunch of them, you'll see it. It goes this far, and then it starts duplicating. So you can see the row. Here's the tail of it, and here's the loop of it. And you can now play with it. I gave you a bunch of challenges where you try more and more various versions of this to find out how the loops work. It's all totally deterministic. And it's again, that's why I love Python in this class. You only need a few lines of Python to do these encryption routines. That's why the programming is easy. It's just the concept you have to get right. If you were paying attention to which cipher you're using and which key you're using and such, that's the important part. And the coding is trivial for simple cases.
So why is that? Because you're using the same algorithm and the same input eventually?
Exactly. Using the same hash function and the same input. Hash functions are not random. They're deterministic calculations. So if I start from A, you can start from a different letter. But if I start from A and just hash it over and over, I'll get the same series of numbers. It's like a seed. But what's interesting is that if the hash function is correct, the output is essentially random. And therefore, sooner or later, it will collide. And then you're just stuck in an endless loop because it's all deterministic. And that lies, a whole bunch of attacks are based on that principle. That turns out to be a way to avoid consuming a ridiculous amount of memory when attacking things.
It lowers like the variance, right? Or it lowers the possible.
It means that you know you'll just come back to the same numbers over and over. So if you just remembered every 10th one, you'd eventually hit it again anyway. Mm-hmm. And so it means you can take a little longer to save a lot of memory. And that turns out to be the opposite of the previous time memory trade-off, where you use a lot of memory to save some time. Sometimes the memory is the constraint, and you're willing to take more time to take less memory. So it lets you turn that dial. And that turns out to be very valuable for certain problems. Anyway, so check it out. I guess I'll stop the share unless I see a question pretty soon. And then I'll just go upstairs to the lab and help anybody, if anybody wants to work here. We're supposed to have torrential rain, but it doesn't seem too bad out there. Anyway, I'll see you next week, I guess. And our time will be gone this weekend to glory in the CCDC. So congratulations, they're here. They won one contest and placed in another to move forward. So we're getting a lot of attention around here as the victorious cyber warriors. So that's good for us. Anyway, all right.